Welcome to our second encounter with the Photon Epoch. In this video, we're going to explore everything about the Photon Epoch other than the nucleosynthesis that goes down from 1 minute to 20 minutes in. And that means that the main things that we're going to be looking at are the transition from a radiation-dominated universe to a matter-dominated universe at 57,000 years, and that's going to bring up a conversation about how the structure of the universe, really the density of the universe, is changing from place to place during this epoch. We're also going to take a look at the substance that exists during this epoch, and then we're going to move towards 380,000 years, which marks the advent of the next epoch. Let's get into it. 20 minutes in, with nucleosynthesis over, what does the universe look like? The universe is continuing to expand. It's filled with the plasma of hydrogen, deuterium, helium-3, helium, and lithium, with loose photons and electrons, and those photons keep on running into charged particles such as electrons and protons, which deflect those photons, which means that the photons can't travel very far. In other words, the universe is foggy. It doesn't let photons freely travel. This plasma continues to thin out as the universe expands, and this will bring us up until 57,000 years. And at 57,000 years, something major happens. Matter becomes dominant. There's more matter than there is radiation. The radiation has thinned out to the point that matter, meaning dark matter and ordinary matter combined, sums to more than the total amount of energy represented by radiation. And this really changes something. In order to understand this change, we have to understand what was going on from the end of inflation to 57,000 years. During this period where the universe was dominated by radiation for most of it, from 10 seconds to 57,000 years, and even prior to 10 seconds, it was dominated by relativistic particles. Particles, even if they're matter particles, that are moving at the speed of light. And the thing about relativistic particles is that in a sphere dominated by relativistic particles, the acceleration of the universe decelerate and it slows down very, very rapidly. But the moment we mark that transition to a matter-dominated universe, that deceleration continues. It continues slowing down, but it's slowing down at a bit of a slower pace. It's not slowing down as rapidly as it was slowing down prior. Also, when you're in a radiation-dominated universe, matter can't clump up easily. Gravity doesn't do its thing in the normal way. In the way that it would if not for the fact that the universe is dominated by radiation. So when the universe is dominated by radiation, the kind of world that we're familiar with, where you'll have, here's an area and it's filled with matter, and here's an area that's less filled with matter, some of the matter from this area will be drawn to this area because this is more dense, and that means that across time this area will become more and more dense and this area will become more and more empty. But in a radiation-dominated universe, that's not allowed to happen. That's prevented from happening. And instead, the only differences in density that you see comes from the relationship between the amount of matter in any given region and the expansion of the universe. Because matter has the effect of pulling back on expansion and preventing expansion from going as fast as it would go, that means that a region with more matter will be pulled back more than a region with less matter, which will have an easier time expanding. And that means that this region, which already was slightly less dense than this region, will be even less dense relative to this region after a little bit, because this region doubled in size, let's say, and this region only went 1.5 times its size. So this region, which was already more dense, is even more dense relative to this, although obviously both regions are less dense than they started off. The point is, even without the kind of growth in density that we're more familiar with, the differences in density from place to place actually do change throughout this time period, and once we have 57,000 years, that changes. When matter takes over at 57,000 years, gravitational attraction can now work, can now pull things from less dense regions to more dense regions. But it could only do so for dark matter. It can't do it for normal matter because even though the universe isn't dominated by radiation, there's so much radiation that the pressure imposed by the radiation onto the matter particles prevents the matter particles from clumping up, and instead the matter particles are falling into the denser regions of dark matter and then bouncing back, falling in, bouncing back, falling in, bouncing back this entire time period from 57,000 to 380,000 years in. But for the dark matter, it can do the kind of growth that we were talking about, that normal gravitational growth. So from 57,000 years in, the dark matter begins to clump up gravitationally. Because gravity travels at the speed of light, this kind of gravity pulling from one region to another can only happen if the entire region is smaller than the speed of light times the history of the universe, the amount of time that light had the chance to travel from one place to another, or in our case, the amount of time that the graviton, which moves at the same speed as light, had the chance to move from one place to another. In other words, within the light horizon or the graviton horizon, this kind of normal growth is happening, but beyond that horizon, only the kind of growth that I mentioned earlier, which is called super horizon growth, that growth that comes from pulling back on the expansion itself, only that kind of growth could happen. But as the universe expands, at this point, it's moving slower than the speed of light. And that means that increasingly the horizon sizes are getting bigger, because light is traveling faster than the universe is expanding, so the horizons within which dark matter is clumping up at this point, those horizons are getting bigger and bigger. Now we're going to make the transition to leaving the photon epoch, so let's get our bearings on the story of it again. The nuclei, the photons, the electrons, they continue to get more and more diffuse as the universe expands throughout this epoch. From 57,000 years in, gravity is able to take over, at least for the dark matter. Still, the pressure from radiation is preventing the standard matter from clumping up. The photons, as the universe expands and cools, continue to lose energy. From 20 minutes to 600 years, they were X-rays, but at 600 years, they switch to ultraviolet light. That goes on to about 50,000 years in, at which point it transitions to green light until 90,000 years, when it becomes yellow, which goes until about 260,000 years. Then the transition to orange takes place, and that lasts until the end of this epoch. At the end of this epoch, around 380,000 years, we're looking at, because of these photons, a universe that is colored a dull orange. And it's at that point, at 380,000 years, that the plasma that we've been dealing with until now begins to disappear and be replaced by a gas. That's the story for our next video on the cosmic microwave background. Till next time.